Welcome to homework.
Here, in this question, before calculating the period of vibration of the system, first we draw the free body diagram of the given system, which can be shown below. Now, we are going to calculate the moment of inertia of disk about the center O by using the relation I/O equal to mr square divided by 2. Now here I/O is the moment of inertia of the disk, m is the mass of the disk, and r is the radius of the disk. Now here we substitute 20 kg for m and 0.3 meter for r. Therefore I/O is equal to 20 multiplied by 0.3 whole square divided by 2. Thus, I/O is equal to 0.9 kilogram meter square. Now, first we write the relation of the displacement in the spring due to the small angular displacement, that is given by S equal to R theta. Now, here theta is the small angular displacement in the spring. So, we substitute 0.3 meter for R. Therefore, S is equal to 0.3 theta. Now, the relation for total displacement in the spring is given by y equal to y of st plus s. Now here y of st is the static deflection at the equilibrium. Now on substituting 0.3 theta for s in the above equation, we get y equal to y of st plus 0.3 theta. Now we write the equation for the force in the spring. So the force in the spring is given as Fs equal to Ky. Now here we substitute the value of y from the above equation. So we get F of s equal to K multiplied by y of st plus 0.3 theta. Now here K is the stiffness of the spring. Now on applying the equation of motion for the system, we get sigma m naught equal to sigma m k, or we can write this as mv multiplied by g multiplied by r minus k multiplied by y of st plus r theta multiplied by r equal to I naught alpha plus mv a multiplied by r. Now here we substitute r alpha for a. Therefore, mvg multiplied by r minus k multiplied by y of st plus r theta multiplied by r equal to I naught alpha plus mv r alpha multiplied by r. Now, here in the above equation, capital M is the moment and A is the acceleration of the block, alpha is angular acceleration of the disk, mv is mass of block, g is acceleration due to gravity, r is radius of disk, capital K is stiffness of spring, theta is angular deflection, and y of st is static deflection at equilibrium. So we substitute 0.9 kg meter square for I naught, 4 kg for mv, 20 kg for m, 9.81 meter per second square for g, 0.3 meter for r, and 200 Newton per meter for k. Therefore, we get 4 multiplied by 9.81 multiplied by 0.3 minus 200 multiplied by y of st plus 0.3 theta multiplied by 0.3 equal to 0.9 alpha plus 4 multiplied by 0.3 alpha multiplied by 0.3. So from above, we get 1.26 alpha minus 11.772 plus 60 y of st plus 18 theta equal to 0. Now let it name the equation 1. Now for equilibrium, substitute 0 degree for theta and 0 for alpha in the equation first. Therefore, we get minus 11.772 plus 60 y of st equal to 0. Now, from above, we get 60 y of st equal to 11.772. Now, we can obtain the equation of the motion of the system by substitute 11.772 for 60y of st in the equation first. So here we get 1.26 alpha minus 11.772 plus 60 y of st plus 18 theta equal to 0, or we can write this as 1.26 alpha minus 11.772 plus 11.772 plus 18 theta equal to 0. Now, after simplifying this, we get 1.26 alpha plus 18 theta equal to 0. Now, here we can substitute theta dot for alpha. So we can write the above equation as 1.26 theta dot plus 18 theta equal to 0, or theta dot plus 14.2857 theta is equal to 0. Now let it name the equation 2. Now we write the generalized equation for the single degree of freedom vibrating system without damping, which can be written as follows: theta dot plus omega square n theta equal to 0. Now let it name equation 3. Now on comparing 3 and 2, we get omega square n equal to 14.2857, or from above we get omega n is equal to 3.7796 radian per second. Now we are going to calculate the natural period of vibration. So the natural period of vibration is given as tau equal to 2 pi divided by omega n. Now here on substitute 3.7796 radian per second for omega n, we get tau equal to 2 pi divided by 3.7796. Now, after dividing, we get tau is equal to 1.66 second. Therefore, the period of vibration of the system is 1.66 seconds.